Łagoda. We are from University of Technology in Poland. Before we had some papers about steel, now we have composite material. The plane of presentation is multi-axial fatigue criteria in plane stress state. Next, some words about fatigue test of laminators. Next, application of the multi-axial fatigue criteria in the critical plane for composites, and verification of multi-axial fatigue criteria for composite laminates. And on the end, some conclusions. It is necessary to remember that usually for composite material we don't use standard notation. As you know here, usually is void notation is standard. But we have plane stress, so we will have only sigma 1, sigma 2, and sigma 6 is shear stress. The most popular strength criteria for composite materials is the maximum strain. But in this paper we don't use this criteria because the control was stress, and it is impossible so easy to change from stress to strain in composite material. So other interesting criteria is maximum stress, acid psi heel, psi wu, and some others. So very often is used acid psi heel for plane stress. You may write this equation as here. Noise equation is very similar, only the changing is this third part of this equation. And next is maximum stress. So you see that is the most important criteria in using in composite materials. So in this time we compare amplitude with three direction with three stresses and looks which is the first will be crack. So it's possible to calculate amplitude of equivalent stress. This is the same for metals. So let's say here amplitude of equivalent it will be put as here. As I told, noise is also very similar, and for maximum stress the equivalent amplitude you may put as maximum of 3 parts. Where we find the maximum, it will be this stress it will be the most important. The material it is laminates. You may see the schema of this material. All data are the source are from the Greek scientific Philippines last year proposed, and it was published in International Journal of Fatigue. This material was also analyzed in other paper by these authors. The end quantity of spacement was 0, so in direction 1, and next 30, 45, 60, and 90 degree. 90 degree is this direction. And we did calculation. You have Pascal equation. We calculated sigma F and B for every position of cutting spacement, and we calculated because we see that it's nearly parallel. So of course it's not the same, the slope, but it's very close, so you may say that it's parallel. It's typical for materials, but sometimes it's not true. And the mean lifetime in this regime was 10 power 5, so we calculated amplitude of stress amplitude for 10.5. It will be important to calculation some parameters. Up to this is from literature. We need some calculation. But what is new? Of course, here it's this x, y, s. It is the stresses in x, y, one direction, 6 direction, and shear. This is no universal proposed in literature. In this source, it was calculated as here. And next, it is necessary to using x divided by y and x divided by s. And next, it is equivalent normal stress in the critical plane defined by maximum normal stress. Up to this day, I use this criteria for some metals. Steels, aluminum, gas iron, also welding. But now we tried to using this for composite material. First part of this, it was presented in Catania last year, but it was using also only we calculated normal amplitude, and we looked on which plane we obtain the maximum amplitude of normal stress. But it is also possible to calculate shear stress and look on which plane we obtain maximum shear amplitude. You will see that original from the physics, it will have here divided by 2. But when we calculate it, we see that on this situation we don't obtain good results. It was necessary to divide it by 4, so 2 times more. This same, we check for shear stress. So next, we did calculation on which direction is alpha we obtain maximum normal stress. You have here from 0 to 90 degrees. And also we did calculation for every spacement where you obtain maximum shear stress. It is from minus 45 up to 45. So you may see that it's very easy to move one equation up to here. We see equation first, equation second is the same, minus 45. And on the end, after calculation maximum normal stress, we obtain this situation, and also by defining maximum shear stress. So in maximum normal stress, you have only maximum normal stress, not more. It's the same for metals, and when the critical plane is defined by maximum shear stress, we calculate it is the sum of shear stress in this critical plane and the normal stress with some coefficients, typically. And that we did calculation of, here's number of sides, here is equivalent stress amplitude in megapascal, and always here you have equivalent amplitude of stress. And in every figures we obtain angle of cutting of spacement up from 0 up to 90. The main line, it is for 0, it's basic. So we see this for the ATH hypothesis, we have such situation. Next, using Norris. Whereas Norris is more closer to the basic figure line. Next, maximum stress. For maximum stress, we see that, for example, for 45 degree cutting, the equivalent amplitude is too small, for example. Next, we define it is a calculation maximum amplitude defined in the plane of the maximum normal stress. We see for this situation, for example, for 30 degree cutting, the amplitude, equivalent amplitude is too small. And next, it is this new, it is the critical plane defined by maximum shear stress, and we obtain a calculation from sum on normal and shear stress. But now we have many points. It's difficult to say what is the best. It was very difficult. So it's necessary to do some statistic calculation. And we did such calculation. It is sum of quarter logarithm sigma experimental divided by calculation, divided by number as calculation, and next because it was in logarithm scale, it's necessary to calculate 10 power this equal. And we see 5 possibilities, and for the ATH criterion, this parameter is not good. The best will be 1, of course. Never you obtain 1. And we see that using this new criteria, critical plane shear, we obtain the best results. Other calculations are between these two possibilities. So, because of, as I told, from the figure, it wasn't possible to say what is the best. So, conclusion I put in my presentation, but in one slide we have this the main conclusion of our calculation. Application of the ATH criterion have the worst complications of the calculation with the results of experimental studies. The newly proposed criteria in the critical plane defined the maximum shear stress, giving the best result. In the criterion defined in the critical plane, we use the coefficient of the influence of normal and shear stresses. Those coefficients were defined based on values of X, maximum normal stress in main direction 1, and S, maximum shear stress in plane 1, 2. The proposed criterion can be used the essays to fatigue-like in complex operation or non-proportional load states. But it's for the future, of course. Thank you for your attention.
Thank you for the nice presentation. Do we have any questions? Okay, I have a question, maybe an observation about the maximum shear stress. When you show the diagram with all the scatters, I noticed that the go back a few slides. That one, no, figure 6. Yes, it was the only
Shear or normal?
maximum, the previous one.
Okay.
Okay. Oh, sorry, my bad. I meant to say figure 6.
Maximum.
Yeah, because I noticed the 45 cutting degree. That was the only case where they were all well below the rest. Usually they were on top or much higher. So is there any special reason for that?
I don't know. Maybe at the beginning it was better to do experimental for not so complicated composites. But in literature you find this, and we did such a calculation. But I think it would be good to calculate it, for example, in one direction. It will be necessary to do such an experiment.
Okay.
Or find in literature, of course.
It was interesting to see that one was different from all the rest.
Yes, yes.
Okay, thank you. If we don't have any, okay, thanks again. Okay, we can move on to the next presentation.